Introduction. Can everyone hear me in the back? Think so? Okay. So yeah, I'm Benjamin Nuernberger. I'm presenting our work on SnapToReality. So positioning virtual content is important in many augmented reality applications with respect to the real world. So for example, we have this virtual recipes app here centered nicely on the cabinet doors in the back. We also have this vacation to-do list application positioned nicely near the corner of the refrigerator. And similarly, we have the Maui weather app positioned nicely near the corner of the table. And this is just one example where precise positioning of virtual content with respect to the real world is important. And in the physical world, we often take this for granted. We can place things in the world with respect to certain physical constraints or design constraints. Another scenario is in authoring or creating virtual content. So say you want to create a toy in this room, let's say Thomas the Train on this sofa, and we want to move this virtual Thomas the Train off the sofa onto a virtual bridge. So you might start by first building up the columns of the bridge to the height of the sofa, and you keep going, and we build out these columns, and then you extend the bridge from the height of the sofa onto these columns. And then now your Thomas the Train can easily and seamlessly move from the sofa onto the bridge. So these are the kind of experiences that we want to create. So we asked ourselves this question: how can we precisely align virtual content with respect to the real world, given certain physical constraints or certain design constraints? And we quickly realized that an important tool in many desktop 2D and 3D environments is snapping. So snapping, you're probably all familiar with it in different applications such as PowerPoint. Here you see PowerPoint allows you to snap virtual content with respect to certain geometrical properties of other content. And of course, snapping has been researched many years, and due to limitations on the time, I'll just give you two examples. Beer's work in the late 80s on snapdragging is one of the early works, and today we can play with tools such as SketchUp, where you can extrude different content to snap to the height of other content. Now this is in the realm of snapping virtual content to virtual constraints. Our work is actually in the realm of snapping virtual content to real constraints. So in this realm, we have a line of work with 2D image snapping, starting in the mid-90s by Gleicher. And more recently, Lee and Billinghurst applied this in augmented reality to an augmented reality drawing application. Similarly, in the same year, in 2012, Nuernberger in Korea analyzed a single image, extracted different image features such as vanishing points, and use those to place virtual content in that single image. Our work actually takes this a step further, extracting these 3D constraints in real time for 3D augmented reality snapping. And I'd like to point out here that snapping to virtual constraints is inherently easier than snapping to real constraints, because in the latter case, you need to extract these real constraints from the real world in real time. And we'll talk a little bit more about this in a moment. So I'd like to show you here a video of our system working. And this is actually a Unity screen capture that shows the scene captured live by a mounted Kinect camera. And it's overlaid with augmented reality visualizations. And in a couple slides, I'll show you our actual augmented reality view. But suffice it to say, notice how the user is building up virtual roads that are snapping to be parallel or perpendicular to the edges of the table. And our system extracts linear edges and planar surfaces in real time for snapping to. And our results in this paper show that our system can extract these linear edges and planar surfaces that people would want to use for snapping, and that snapping in augmented reality is faster than no snapping for positioning and orienting tasks. And we'll also see that enables new forms of creating virtual content. So with that, let's talk about the prototype. So our prototype system hardware is composed of a Loomis optical see-through head-mounted display, wireless remote for interaction, a Kinect camera mounted above the user, and an OptiTrack system for tracking the user. But we imagine that this would be implemented on a fully contained wearable device such as HoloLens in the future. This is the view on the left here through the optical see-through display. And note, due to the HDR nature of the capture system that we use to capture through this display, we're mainly going to be showing images like that on the right side for the rest of this talk. And again, those images on the right side are a live capturing of the world from a Kinect camera that is overlaid with virtual content. So again, we extract linear edges and planar surfaces as our physical constraints. You can think of other constraints such as curved surfaces, but linear edges and planar surfaces are a subset that is simple, but it's rich enough and contains a lot of semantic information. So the linear edges we extract from the Kinect camera using Huff transform, followed by some post-processing. Then we extract the 3D line segments, followed by temporal filtering to reduce noise and also adjust to the dynamically changing world, as you can see here in this video. And this runs in 15 frames per second. The planar surfaces, again, we run another Huff transform on the depth image, and we follow this by greedy agglomerative clustering. And this runs in 4 frames per second in our unoptimized implementation. So with that, we can now talk about our snapping algorithm, which is, I'll say it's a vanilla standard snapping algorithm, but in this scenario, it's unique. So say we have our virtual cube here, and now we have, in this cube, I'm calling these virtual constraints, namely these edges and these planar surfaces. So these are the virtual constraints internal to this virtual object. Now we want to snap this virtual content to the real world. So say, and again, this real world has real constraints. So say we're focusing on the table, and the table has these set of edge constraints and this planar constraint. And now we want to snap this virtual content to be in this target snapping position. So this is our goal. So the way it works is we snap using the pair of compatible constraints with the lowest cost. And what do I mean by this? I'll explain in the context of the algorithm. It's pretty simple. So we first search through all the virtual constraints, and we check to see if it's compatible with any of the real constraints. So say we're looking at this red virtual constraint. And we check all the real constraints, these real ones, and say now we're focusing on these 2 red edges. So we check if they're compatible by making sure that they're close enough in distance. And if so, we use as the cost a linear combination of this distance and that arrow there, and also the distance between these 2 constraints to the exact centroid of the real constraint. And we can do something similar with planar surfaces, such as these 2 planes. And then that's the real plane extending out. And then we use that these 2 distances for the cost. And I'll refer you to the paper for more details on this algorithm. So with that, now we can talk about some user evaluations. So to evaluate the constraint extraction, there's many different types of lines and planes you can extract from the world, but we wanted to see what users thought would be good for snapping virtual content to. So we explained a simple scenario such as snapping your virtual application windows to different things in the scene. And we gave users, 4 participants, 11 scenes, and asked them to draw on these 11 scenes the edges and the planar surfaces that they would use for snapping in this context. So this is an example where they snapped. This is an example of lines they drew, edges they drew. These are planes that one user drew. And we aggregated this over the 11 scenes. And our algorithm can detect the majority of the edges and planar surfaces that the participants indicated they'd use for snapping. So then we evaluated our SnapToReality techniques. So the first application was AR content placement, and the second one was AR content creation. For AR content placement, we wanted to see how fast users can place, orient, and resize different virtual content with respect to the real world, with snapping and without snapping. So in this example here, you see that the user is picking up a virtual application window, and then it has a target ghost window that they have to match first in position and orientation as the first part of the trial, and then next in size to resize. And we gave users 20 trials, 10 with snapping and 10 without snapping. Here you see the no snapping condition, and notice in this one the virtual content does not snap in position or orientation to the real world. It does, however, it is placed at a distance that is at the depth of the user's gaze intersection with the environment. But other than that, we did not change anything between these 2 conditions of the snapping and no snapping. And we measured task completion time across all of these. We also gave users 5 training trials before each of these conditions and balanced the conditions completely. This is the view through the optical see-through display. And notice it's actually not that bright to the user. It's just the limitation to how we captured it through the optical see-through display. This is our second demo application, AR content creation. So the user draws out a rectangle on a planar surfaces and then can extrude cubes to different heights, snapping to different areas of the environment. Here you see the user drawing out some virtual cubes. And we noticed that with this kind of dynamic extraction of constraints, users can now use different objects in their environment, such as this physical measuring tape. So first, you see here on the right that the virtual cube is snapping to the height of the box, and then it snaps to the height of the measuring tape. So timing results for the demo application 1, we saw that there's a statistically significant difference in the time for positioning and orienting. Snapping took about 4.5 seconds, and then no snapping took about 11 seconds. However, in scaling, we didn't see any statistically significant difference, and we think this might be due to the scenario that we chose. And also, our scaling is actually, if you think about it, it's a 2D scaling. It's not really a full 3D scaling. Something else that is interesting is that we observe the user's physical movement between the two conditions. So, using snapping on the left, we see the user moved a lot less than without snapping, on the right. And we think this strongly exemplifies the importance of bringing different techniques into augmented reality, such as snapping. And we think this is good to explore in the future. So there are some questionnaire results. I don't have too much time to go into it here, but you can look at the paper for the details. But suffice it to say that there's a statistically significant difference between the snapping and the no snapping. So for example, users rated that they could place objects more easily with snapping than without snapping. And you can see the paper for more details on this. Finally, I'd like to share with you some design considerations for SnapToReality systems and future developers. So first is the limited user field of view. We don't necessarily mean the limited display field of view, as we saw in the previous talk, but even with a perfect display, how would the user know about the constraints behind them outside the field of view? And how do they select the constraints that are outside the field of view? One way here we offer to suggest is perhaps the user can actively select the constraints rather than passively just moving the object around close enough to that constraint. Second is changing the view in AR. In augmented reality, the users are limited by the physics of the real world. If you want to look at something closer, typically you move up to it to be closer. And this is something that we should consider more for the future. The camera field of view, mainly what I mean here is the camera has to first sense the environment to extract these constraints. So the user must move the camera or let the camera sense this world before he or she can use these constraints. Noise and complexity in the constraint extraction. The sensor might have some noise. This environment is very complex. So one potential solution would be to have some user-in-the-loop disambiguation. So future SnapToReality systems need to design how they extract these constraints with this in consideration. Again, dynamic constraints, I mentioned this earlier. It might not be obvious at first, but now that we can extract these dynamic constraints, we can use physical measuring tape to create new constraints on the fly, and this will guide the formation, the creation of virtual objects with respect to the real world in augmented reality. And finally, constraint visualizations. So on the left here, you see our visualization for the edges that you're snapping to. On the right is for the planes. For the planes, I'll explain it. We have a fuzzy circular region placed at the centroid of the plane, and then a red line connecting the virtual content to that centroid of the plane. And one consideration here is, do you visualize all the constraints? Do you visualize none of the constraints? Or do you visualize just the constraints that you're snapping to? In this work, we just visualize the constraints that we're snapping to, but it's something to consider for the future. And final thoughts. So for future work, we think it would be interesting to explore interaction via other modalities, such as using hand gestures or eye gaze for actively selecting the constraints. You can think about touching the constraints. Speech recognition. If your camera has sensed the environment, wouldn't it be nice if you can just say, place this object to the right, parallel to the right of the door. Also filtering constraints. if you're snapping to a constraint that's behind you, you might not want that. So we need to consider what are other ways to deselect or undo different types of constraints. And again, there's more types of constraints out there. There's curved surfaces, semantic snapping. One example of semantic snapping is, say you have a recipes app, like in the first example. Your recipes app might want to be favored to be placed on the kitchen cabinet rather than on your fireplace, for example. So thinking about ways to bring semantics instead of just simple geometric snapping into augmented reality. So with that, I'll conclude. So we presented our SnapToReality concept and prototype, and we showed that we can extract the majority of constraints that users say they would use for snapping. We've confirmed that snapping in augmented reality is faster than no snapping for positioning and orienting tasks, and enables novel ways to interact with creating virtual content. Thank you.